Hey everybody, it's Ripley back again. So what we're going to do today is we're going to talk about assessing normality. If normality is so important, and you're going to see how much more important it is than a whole lot of things in the upcoming sections. And I don't mean to be passive aggressive or elusive, but it's really true. So what we're going to do is we're going to talk about something called assessing normality. Sorry about my handwriting. This tablet Normality is kind of a pain in the butt when I'm recording because it's such a RAM hog. All right, now, excuse me. What we're going to have is what we're going to use is called a normal quantile. Wow, this thing is really lagging today. Sorry. Plot. And what it's going to be is it's going to be a box plot, but it's real simple. It's a set of points, x and y, where x is just the original data. So you take a sample from a population, and this is just going to be the data. And I'm going to show you how to do this on your calculator because there's pretty much no way that you want to do this by hand. It's awful. And you might have an instructor that teaches you how to do this with a different software package, but you can do it very quickly on your TI, which is lovely. And then this is what y is going to do. What's going to happen is the algorithm is going to spit out the corresponding z-score. Corresponding z-score. Okay? So what it does is it takes all the data, it crunches it, and then it finds z-scores for them, and then sticks those into y's, and then it plots it. Okay, but this is going to be the easiest way to assess for normality. Okay, but let's talk about, well, I guess there are easier ways, but let's talk about just we've got a data set, right? Any data set. What's the easiest way to say, okay, this looks approximately normal? So any sort of assumptions of normality can be met or approximately met. Well, the easiest thing is always look at its histogram. I mean, if I've got a histogram that looks like this, you know, something looks pretty good, this looks all right, we'll stick another guy here and another guy here. It's like, yeah, that's approximately normal. I mean, it's close enough. Remember, this is made by samples, right? So we're pulling out samples. So unless I were to pull out a whole bunch, excuse me, unless I were to pull out a whole bunch of data, close to what, I don't know, let's call it 2/3 of the population. I am pulling that number out of my ear. You know, if I've got a sample size of, say, 20, and it looks like this, you're in pretty good shape, true? Also, I know that if it's a sampling distributions automatically converge to a normal distribution by the central limit theorem, which we love, right? As long as it's a true sampling distribution. All right, the other way, excuse me, the other way is that we got to worry about normality is outliers. Always. Remember, outliers are definitely a main trope that we deal with in statistical analysis of data because outliers can really screw things up. In other words, if I had an outlier like way out here in my histogram, well, now I've got a problem here because where I used to have this sweet little normal-ish looking curve, that should have dropped down here. Now I have this heavy skew left. Excuse me, heavy skew right. That's where the tail points, right? So the way to really, as always, when we get an outlier, we get something that's apparently outliers, and we know there's lots of ways to analyze for that. Remember the 1.5 times IQR, add that, and subtract it from your third quartile and your first quartile, respectively. Ways to determine outliers, which we then analyze, and we decide if we're going to keep them or not. I know that feels arbitrary, but it isn't. Trust me. It's a good thing to be able to throw outliers out because there's sampling error, right? We have to make sure that we're careful about things like that. Okay, sorry. Let's get back on track. So I'm just simply going to show you how to make a normal quantile plot. And then that's about it for the video. It's not very hard. Now, when I do this, I'm going to use my TI, and I've already sort of cooked up. A data set. So bear with me here. Sorry, there's people working here, and it's insane. All right, so I know I hate it when people work at my school. Ugh. So anyway, I'm going to go to Stat, and I'm going to edit. So I'm going to hit 1, and I'll show you the data set that I've already got. So my data set is 1155788. And I'm not going to bore you with making a histogram from this because you can probably see what's going on. Then I've got 10, 10, 10 Clearly. So let me do that again. Excuse me. 11557881101010. So you could build a really quick histogram of this if you wanted to. But I'm going to show you how to create a normal quantile plot, especially in your calculator, so you can do this really quickly. So what we're going to do is we're going to go to second, stat plot. All right, and then I've already played around with this thing just a little bit, but I want to show you what I did. First thing I want to do is I want to turn it on. So I turn it on by hitting enter. All right, and then now notice what we would typically do if we just wanted to do a scatter plot. We would use this guy right here. Time series would be here. Histogram is here. Box and whiskers are here, or just box plots. This guy's with outliers. This guy's without. And then there's this magical little guy right here. Now notice if I toggle over, notice that the input, whoops, I don't want that. Go down, Ripley, you moron. All right, let's say that I just hit here, enter. Now notice that, let's see, oh, I'm still in, dang it, sorry guys. I gotta go up here, back up here, and hit, let's see if it's gonna, there we go. Notice this is what we're typically used to dealing with is L1, L2, which you'll get way more into that with linear regression. I gotta go back up here. You know what the pain in the butt of this is, especially with this emulator, is I can only go in one direction. When I hit enter down here, now it's only using one data set, right, as opposed to bivariate data, which would be L1 and L2. Now, what we're going to do with normal quantile plot is I'm going to go over here and I'm going to hit enter. All right, now it only asks me for, I'm going to put L1 right here, and then excuse me, once I hit enter here, oh, I'm already there. I've got L1, that's where my data was. My data axis is I'm going to leave it as X, Y, so the defaults are all set up. And then you can use whichever one of these you want. I suggest using either the plus or the square. I like the square because the square is easily seen. All right, now if I simply go, remember when in doubt, quit out. If I quit out to my home screen, ooh, look at that. That's some impressive mathematics right there. Let's clear that. And I go to Y equals. Two things, for those of you that are taking other courses other than stats, you got to remember to check to see if these plots are turned on. If the plots are turned on and you try to graph a function, all hell's going to break loose because the computer's not going to be able to graph everything that you want. So the easy way to do that is to simply, to turn it off, excuse me, is to go up, hit enter, and it's off now. But in this case, I want it to be on, so I hit enter. Now, remember, your calculator is doing an algorithm. Right? And it's actually autofilling. If I go back to stat and I go back to edit, notice all that I have is a data, or one data set, L1. There's nothing in L2. And the reason there's nothing in L2 is because I haven't technically told the computer to do anything yet. I'm going to do that right now. When in doubt, quit out. Now the way that I do this is I hit, this is very weird, you've never seen this before. I hit zoom and then I hit stat, which if you recall, I'm going to go up. It's probably easier to go down, who cares? What I'm going to do is I'm going to go up to zoom 9. What just happened? Sorry, guys. Oh, there's zoom stat right there, and I hit enter. Bam! And it graphs it for me, which is really cool. Okay, now let's analyze this graph. Okay, now again, you haven't really gotten into this yet as far as trend lines or least squared regression lines because that's later in the class. But look really closely. I want, if this is normal, I want all of these to be on a line. I want them to be approximately linear. All right, I don't like this guy, and then this weirdness over here, which kind of makes sense, right? Because those 10s that I had, they're going to have the same z-score. Also notice these z-scores. This is 1, this is 2, this is, oh, sorry, these are, wait. I got to make sure I know. Yeah. Sorry. When it distributes these, don't listen to me. But all that we're looking for is a linear relationship between the data values. It stacks these things the way it is based on their relative z-score. So all that you're looking for is linear. This is not linear. They're not on the same line. And predictably, like we just said, it doesn't appear as though that data is normally distributed. Okay, now that's just the data, the sample data itself. Now look, I forget how many values I had. Let's go back to stat really quickly and edit. How many data values did I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I had 10 data values, right? Because of the 10s. If I go up or if I go down, because of the 10s. Let me make sure. I think I had 10 data values. Now that's a pretty small sample size, right? So as we get bigger sample sizes, those sample sizes, if we're not talking about sampling distributions, we're just talking about larger sample sizes. If those samples come from a normal population, then the data should appear to be more normal. All right. So this is a kind of a very clever way to test normalcy or normality, excuse me, of a data set. Okay. Now, I realize, don't let this confuse you with the central limit theorem. We're going to have all kinds of error in our samples, right? When I grab samples, my sample is not going to equally match or nicely match my population because of error, true? But watch if we gather a bunch of data, a lot of data, thousands of data points, and we're like, I wonder if the waiting times in a line at a grocery store are normally distributed. And I'm going to sit here and I'm going to gather 2,000 data sets, or excuse me, data values, and then I can check them for normalcy relatively easily. Now, watch this. I'm going to change this data set. I'm going to make something that, let's see if we could make this thing look approximately normal. Okay, so what I did is I tweaked the data set. Sorry for the abrupt cut, but apparently I don't know how my calculator works. Don't ask. Anywho, so what I did is I tweaked the data set. So instead of that old data set that we had, which was clearly not normal, what I did is I noticed the data. I went, well, there's 1 1, there's the 2, there's 2 3s, there's 3 4s. I did 5 5s. I just basically brute forced a super symmetric looking data set. There are 3 6s just like there were 3 4s, there were 2 7s just like there were 2 3s, an 8 and a 9. Now, I did do the histogram on this one because it's not a bad idea to review how to do a histogram. Let me show you how to do this. So I'm going to go second stat plot. Notice that I turned my my normal quantile plot off. I'm doing this, I turned on plot 2, which is my histogram. Okay, oops, sorry about that. Something just fell. Now, let's go down to 2, and I'll show you how I edit this thing. So it's real simple. I just turn it on. I put it on histogram, and then just like before, well, we've seen this before, I used L1, which is where I stuck the data, and then I did a frequency of 1, and the frequency of 1 is just the Y value, okay? But I don't know why they're doing that. I hate this thing. Sorry, guys. I get those automatic pop-ups, and there's no way to freaking shut them down. Anyway, so let's get back to this. The trick with having the histogram work the way you want it to is to set the window. Watch, if I just hit zoom stat, which is zoom 9, it doesn't look anything like how the data should. That's because the default settings on the program, on the graphing program, set the histogram widths very strangely. So what I do is I go into my window. I set the min as my min. I set the max as my max, which was it 10? Yeah, we'll put it in as 10. No, it wasn't. It was 9, wasn't it? Because whoops, dang it. Let's go try this again. My min was 1. My max is 9. And then my scale, this is where you set the width, is just 1. All right, now watch when I graph it. It's going to be beautiful. Oh, look at that. Oh, maybe I need to have it go out to 10, don't I? I want this to be pretty. Sorry, you guys I know it's probably driving you nuts, but boom, and here's 10. And now let's graph it. Well, bam! Okay, clearly approximately normal, right? It's beautiful. All right, now let's go. What we're going to do is we're going to look at that normal quantile plot, right? And it should be approximately linear. All those points should be lying about on the same line, or if we drew a line. Again, you'll get into how to draw lines a little bit later, but we'll get to it. So I'm going to do this the easy way. I'm going to turn on plot 1 because I know it's already set to what I want it to be set to. I'm going to turn off plot 2, right? And then I'm going to hit zoom 9, and let's see what happens. Ba-bam. Isn't that beautiful? Those are lovely. And that's it. That's how it works. Now, notice because they're approximately normal, there's nothing spinning off. There's no curve to it, right? You may say, well, what's going on with all of these? Well, this is the computer stacking these things over the top of one another, all right? Just because that's how it's computing the relative z-scores for each one of those guys. Yeah, this is a really great way for you to be able to test the normality of data, which again, I'll finish just as I started. It's really important down the road to be able to assume or to be able to not assume that data comes from a normally distributed population. All right, thank you very much for your time and attention. I appreciate it. Have an absolutely lovely day. Bye.